Hi everyone, our lecture today is about skeletal structure with charged carbon atoms. And we know the carbon in normal case without charge must be tetravalent, okay? Then if we look to this here carbon, that meaning this carbon has two hydrogen on this side. Because in skeletal structure we don't draw the carbon and the hydrogen bonded to the carbon, and just we will draw the heteroatoms and the hydrogen bonded directly to the heteroatoms, and also of course the unshaped of electron to be omitted. And keep in mind a charge on carbon atoms take place of one hydrogen atom. That meaning here in this carbon we have two hydrogen. If we remove one hydrogen, that meaning it will be positive charge. Then here the positive charge on this carbon, meaning we have just one hydrogen on this carbon to be trivalent, not tetravalent. Okay. And look here, we have just one hydrogen bonded directly to this carbon. Of course, the negative charge on the carbon, it is like unshaped of electron. Okay, that meaning the charge determines the number of lone pair. Negatively charged carbon atoms have just one lone pair, and positively charged carbon atom have none. There is no electrons. Okay, keep in mind again the positive carbon atom without electron, the negative charge, meaning two unshaped of electron. And because the skeletal structure omit the unshaped of electron, then don't forget the unshaped of electron. Then if we said OH without charge, that meaning this oxygen atom has two unshaped of electron. And if we said oxygen atom with positively charged, that meaning this oxygen atom has just one unshaped of electron. Okay, to be tetravalent. Look, 1 bond, 3, 1, 2, 3, tri bond. Okay, to be tetravalent. And you have homework here. Draw an all hydrogen and lone pair. Look, I want from you to draw the hydrogen atom, and if there is any lone pair of electron, you have to put it. Okay, and here draw the skeletal structure for the molecular in the part A and B. That meaning here we have condensed structure. I want from you to draw the skeletal structure, and in C or D reverse we have the skeletal structure. I want from you to draw the condensed structure. Hybridization. Okay, he said here, what orbital do the first and second row atoms use to form bond? That meaning to form bond between two atoms, the atoms share their electron. Okay, by what? By their orbitals. Okay, share their electron by their orbitals. And let's begin with the hydrogen, and then examine the orbitals used for bonding. Look, the orbitals used for bonding by atoms in the second row. The hydrogen, he said here, two hydrogen atoms share each their electrons to form the hydrogen gas H2, and for every hydrogen atom use the s orbital, and the s orbital here it will be overlap meaning mixed together like that, overlap with the one s orbital for the second hydrogen to give you this hybrid orbitals with sigma bond. Okay, it is look to the shape of this orbitals is it is like symmetrical cylinder. Okay, and here the electrons, it will be move inside this orbital between the two atoms to be in bonding. A sigma bond concentrated electron density on the axis that join two nuclei. All single bonds are sigma. Okay, don't forget that. All single bond, it is sigma bond. Okay, this type of bond overlap s orbital with another s orbital, we say sigma bond. Bonding in methane, the carbons has 2 core electrons, okay, plus 4 valence electrons. That means 2 electrons in the first shell and 2 electrons in the second shell. Okay, to fill atomic orbital in the most stable arrangement, the electrons are placed in the orbitals of the lowest energy. That meaning this here has lower energy, and here this has higher energy from this. Okay, and to be in lower energy, that meaning 2 electrons, it will be on the s orbital here in the 2s, and the second 2 electrons, it will be in the 2p orbitals, like that. Okay, this lowest energy arrangement of the electrons for an atoms is called a ground state. Okay, that meaning this here, the figure is a ground. Okay, but in the ground state, if you look here, we will be found to make a new bonds with another atom, the carbon, to make a new bonds with another atom. That meaning it will be used the single electron. Okay, and here we have just 2 single electron. That meaning the carbon make just 2 bond with another atom. But in the fact, it is false. It is not true. The carbon make 4 bond with another atoms like CH4, the methane gas. Yeah. Okay. Then in this description, the carbon should form just only 2 bond because it has just only 2 single electrons in the outer shell, in the valence electron. Okay, but really it is not like that. Okay, typically the carbon make 4 bond. Okay, what is the answer for this question? The answer for this question, the electron here in the ground state, one of the electron from the 2s orbital, it will be move up, it will be go to the 2p orbital. Okay, and of course by energy, need energy, and to be in the excited state for the carbon. And here look, we have 4 electrons alone, single 4 electrons. In this case, the carbon here make 4 bonds, needed another 4 electron. Look, here electron, here electron, here electron, here electron. That meaning the carbon in the excited state needed another additional 4 electron to be 8 electron, to be like noble gas, to be in the hybrid rule, to be in the octet rule. Okay, to make 4 bonds with another atom. That meaning the carbon in this state needed an additional 4 electron. That meaning the s orbital here, it will be overlap with the orbit with p orbital to give a new sp orbital. It will be used for bonding with another atom. And he said here the chemists have proposed that atom like carbon don't use a pure s and a pure p orbital. Don't use this s to p orbital. Okay, instead they use a new orbital called hybrid orbital. That meaning this is pure orbitals, and this is the hybrid orbital. For this reason we said hybridization. Okay, hybridization is the combination of 2 or more atomic orbital to form the same number of the hybrid orbitals, each having the same shape and energy. All this having the same shape and energy. Look here, s orbital with a 3p orbital, energy hybridization, it will be give you 4 this 4 new orbitals equal in energy, and that they has the same shape. Okay, look here again s orbitals it is just like ball cycle, and p orbital hybridization, it will be give you a new hybrid orbitals. And here homework for you: what orbitals are used to form each carbon-carbon, okay, and carbon hydrogen, and the CH3 CH2 CH3 propan, and how many sigma bonds are present in the molecule. Okay, think about that, and you can also use the internet to find the answer. And the answer already here in the lecture, but if you don't understand, you can find in the internet. And here the other hybridization patterns, sp and sp2 hybrid orbitals. Okay, we take the sp3, and here we have the sp and sp2 hybrid orbital, and he's here forming sp3 hybrid orbitals. It is just one way that 2s and 2p orbitals can hybridize. He said it is meaning here. Look, we have 1s and 3p. That meaning it will be sp3. That meaning 1s and 3p. And this type of the hybridization, it is called sp3. That meaning use 1s and 3p mixed together to give you a new 4 orbitals. And three common modes of the hybridization are seen in the organic molecules. And here the number of orbitals is always conserved in hybridization. That is a given number of atomic orbitals hybridized to form an equivalent number of the hybrid orbitals. Okay, that meaning 1 2s orbital and 3 2p orbitals to form sp3 hybrid orbitals, and 1 2s orbital and 2p orbitals to form sp2 hybrid orbitals, and 1 2s orbital and 1 2p orbitals to form 2 sp hybrid orbitals. Okay, and keep memorize this table. If you have carbon surrounded by two groups, that meaning the number of orbital used for the hybridization is the 2 orbitals to give you sp hybrid orbital. And if the carbon surrounded by 3 groups, that meaning the number of orbital used is 3, and the hybridized will be sp2. And if the carbon surrounded by 4 groups, that meaning the used orbital 4, and the hybridization it will be sp3 hybrid orbitals. And again we use 2 orbitals, one s and one p, to give you 2 hybrid orbital, this and the sp hybrid orbital. And for the sp2, that meaning 1s and 2p, to give you 3 new orbitals, hybridized orbitals in the hybridization. And here forming 3 sp2 hybrid orbitals uses 1s again and 2p, leaving one of the 2p orbitals pure without any hybridization. And he have one example: what orbital are used to form each bond in the methanol CH3OH. Okay, now for this carbon sp3. Why? Because this carbon surrounded by 4 groups, that meaning it will be sp3. Okay, and this oxygen surrounded also by 4 groups, 1 bond from here and 1 bond from here, and 2 unshaped of electron, that meaning 4 groups. The groups may be atoms or unshaped of electron. Okay, keep in mind again the group. If I say to you surrounded by groups, that meaning this group may be atom or unshaped of electron. Also this, the oxygen, it will be sp3 hybridized. Okay, and this, what orbital are used to form each one? This homework for you. But the important thing, keep in your mind this table again. This table, okay, this table is useful to resolve like this question. And here in ethane and ethylene and acetylene, also again here the carbon is sp3, here the carbon is sp2 because surrounded by three group 1 2 3, 1s and 2p, it will be sp2. And here the carbon surrounded by two groups, that meaning it will be sp hydrazide. And here from this figure, all the bonds in the ethane gas, the ethane gas is the just sigma bonds, single bonds, and all the carbons here, this carbon, both of the carbons atom is sp3, and there are free rotation between the carbon single bond all while there's a free rotation دوران between the two carbons to give you additional configuration. And here in the ethylene he said each carbon is triangle planar. This carbon يعني مثلث على مستوى واحد. Now trigonal planar on the plane, on the one plane, that meaning this atom and this all these atoms on the one plane. Okay, it will be planar مستوي يعني في مستوى واحد. And it will be, look, this carbon surrounded by three group 1 2 3, it will be sp2 hydrazide, and the hybridization use 1s and 2p orbital to for the bonding for the sigma bond, and let one of the p orbital free. This it will be used for pi bond, for the double bond. Look here, this figure again for the trigonal. This the hydrogen and this hydrogen, this carbon and this carbon. Look, it will be on one plane في مستوى واحد. Okay, and we have just one empty p orbital, one empty p orbital. This it will be used for the pi bond, up and down to the plane, up and down to the plane to form the pi bond. And if you have double bond or triple bond, there is no rotation. Okay, يعني لا يوجد دوران بين هذه الكربون وهذه الكربون. There is no rotation between these two carbons. Okay, also the acetylene here, there is no rotation here, but because we have just one group here, it will be not important for rotation. Okay, there is no different configuration. And also in the acetylene here, look, he will be used this 1s and 1p orbital for the sigma bond, and it will be remain two free or two pure p orbital to make additional two bond. Okay, to be one sigma bond here between this carbon and this carbon, and two pi bond up to down to the plane to form the triple bond، يعني اللي يكون الآصلة الثلاثية. اوكي، يعني هذا الأوربيتال وهذا الأوربيتال سوف يستخدم لأواصر باي، للأواصر المزدوجة والثلاثية. If you look to this example, if I say to you what is the hybridization here for this carbon, you will be say there is three groups surrounded for this atom, that meaning it will be sp2. Okay, and for this carbon there is four groups surrounded, it will be sp3. This carbon also sp3. This oxygen it will be sp2 because there is three group. One here it is one atom, and here two groups, it will be sp2 hybridization for this oxygen atom. The electronegativity and bond polarity, he said here the electronegativity is the measure of an atom's attraction for electrons in the bond. يعني هي مقياس لقوة جذب الإلكترونات إلى النواة. Okay, that meaning if this atom has high electronegativity, it will be take the electron inside it. Okay, and it will be the negative because the electron is negatively charged, that meaning the negative charge, it will be partially near from this atom. Okay, it will be partially negatively charged. For this reason, it will be polar. Okay, and the electronegativity indicate how much a particular atom want electrons. Again, this from another point. Okay, and the following trend in the electronegativity are observed in the periodic table. The electronegativity increase across a row of the periodic table as a nuclear charge increase. Okay, that meaning it will be the negatively charged or the electronegativity, it will be increased from the left to the right in the periodic table, and it will be increased from the down to the up. Okay, from the down to the up in the periodic table. That meaning the halogen here, look to this number 4 for the measure of the electronegativity will be 4 for the floor. Okay, this the halogen has high electronegativity if you compare the halogen with the carbon, boron, and lithium. This the metals from the left side. Okay, that meaning the halogen, the oxygen, the nitrogen, the sulfur, all of this atom has high electronegativity. And again, electronegativity value are used in the guideline to indicate whether the electrons in the bond are equally shared. Look, equally shared or unequally shared between two atoms. That meaning if you have two atoms here, and these two atoms they carbon atoms, that meaning it will be sharing the electron between of them equally. Okay, and look here, it will be 2.5 and 2.5, and here also the carbon and the hydrogen 2.5 and 2.2. okay, it is the same. If you compare 2.5 with 2.2, there is no very big difference between of them. Also it will be non-polar because he said here it will be more than 0.5 the difference between the electronegativity of the atom. And here look to the between the oxygen and the carbon. Okay, the oxygen and the carbon, here this bond it will be polar bond. Why? Because the oxygen is high electronegativity if from the carbon. That meaning the sharing of electron here in this area near from the oxygen, it will be more than in this area near from the carbon, and here in this case it will be partially negatively charged. And here look to this sample here. Partial negative, partial positive. Partial negative and partial positive. Partial positive mean an atoms is electron deficient. electron deficient يعني ناقصا إلكترونيا. Okay, has partial positive charge. Okay, not complete positive charge, not positive, just partially positive charge. Okay, and here the negative charge means the atom is electron rich. Okay, has partial negative charge. Okay, not full negative charge. If you say negative charge, that meaning you will be talking about cation, anion. Okay, but here just partially negative charge, partially positive charge. And this homework for you show the direction of the dipole in each bond, label the atoms. Okay, if we said here the hydrogen and the fluor, that meaning the direction of the dipole, it will be here from the hydrogen to the fluor. Okay, and the same thing between the other. Try to resolve this homework for you. Okay, now the polarity of the molecules. We talk about the polarity of the bond. Okay, then if we know the bond, it will be polar or no, then we will decide this the whole molecules, it will be polar or no, the polarity of the whole molecule. Okay, we said here the net dipole of the molecule, the net dipole. Okay, يعني قطبية الشبكة للجزيئة. Okay, then Number one, we have two steps. Use electronegative difference to identify all the polar bonds and the direction of the bond dipole. Then you have to decide the bonds and for the molecule, it will be polar or no, and the direction for the polarity. Step number two, determine the geometry. The geometry, student, is so important to determine the net dipole. Okay, maybe there is a molecule with polar bond, but the geometry for this molecule make this molecule not polar, or make the net dipole for this molecule equal to 0. Okay, then the geometry is so important, and for the geometry again you have to use your imagination to determine the figure or the position of the atom inside the space, and determine the geometry around individual atom by counting groups and decide if the individual dipole cancel or reinforce of the each other groups in the space. Look here to this example for the H2O molecule. Look, the geometry for the H2O molecule, we know it will be tetrahedral, and we have here one group, two group, three, four groups around the oxygen atom. It will be tetrahedral, and for this reason, here we have polar bond, and we have polar bond. The direction of this polarity will be in this side, and the direction to this side. That means the total direction here, it will be reinforce each other. It will be to the up. Okay, this it will be pushed from this side, and this it will be pushed from this side. That meaning total direction, it will be to the up, and the molecule for the H2O, it will be polar. Take the carbon dioxide. Look, this also have polar bond, and here from we have also polar bond, but the both of them cancel each other. Okay, this it will be in this side, and this reverse for the first one. That meaning the total al-muhassila, okay, the total it will be equal to the 0. Okay, that meaning carbon dioxide, yes, has dipole, has polar bond, but the polarity of the molecule, it will be non-polar molecule. Okay, the same thing here in this example. This it will be polar, and this it will be non-polar, because this cancel this, and it will be cancel this, reverse to the direction, and this it will be reinforce each other. It will be polar and to the up, and this also it will be polar, the net dipole, and it will be direction in this side, and also the tetrachlorocarbon, it will be non-polar, because each group cancel the others. It will be equal to the 0, and the total it will be non-polar molecules. Now he have here homework, and decide each one it will be polar or no. Okay, the next subject is the intermolecular forces. Okay, the intermolecular forces يعني القوة ما بين الجزيئات. Okay, القوة ما بين الجزيئات. There are two kinds of intermolecular forces. The dipole interaction. Okay, dipole يعني دو قطب interaction. Okay, look to the HCl. HCl is polar molecular. If you this, that meaning the chloride will be partially negative, the hydrogen will be partially positive. Positive, negative. The positive it will be attract with negative. The negative it will be attract with another molecule for the positive end, and this it will be dipole interaction. طبعا طلب dipole interaction response about the and give different physical properties for the molecules. Here for the acetone also we have dipole here. That meaning we have dipole interaction with other molecules. The second type we have the hydrogen bond. Typically occurs when the hydrogen atom, here the hydrogen atom bonded to the nitrogen oxygen olefluor, okay, or fluor, the electrostatically attract to lone pair of the electron on the oxygen, nitrogen, or fluor of the atom to another molecule. Thus, the H2O molecule can make hydrogen bond with each other. That meaning this hydrogen bond to this oxygen, it will be partially positive, and this partially positive, it will be make hydrogen bond with the lone pair of electron. Look, with the lone pair, this is so important, with the lone pair of the electron for the oxygen atom. And we also have van der Waals forces. Van der Waals forces is are very weak interaction and caused by the momentary change for the electron density on the molecule. Okay, it is dependent on the surface area. Okay, that meaning the large surface area, the large attractive forces between the two molecules, and to give you stronger the intermolecular forces. And here in this example, look to the ethane, ethanol, and this compound, the aldehyde compound. Okay, acetaldehyde compound. Okay, look to the methane gas. The ethane gas. The ethane gas non-polar molecule. Just there is van der Waals forces. Okay, van der Waals forces dependent on the surface area. Okay, here we have polar, and here in the ethanol we have the polar carbon oxygen and the oxygen hydrogen bond. That meaning we have dipole-dipole interaction. That also we have the hydrogen bond also in this part here. In the alkane part we have van der Waals forces. Here also we have dipole-dipole interaction and van der Waals forces without hydrogen bond. Here we don't have hydrogen bond. Here the subject is about the next subject. It will be acid and base, and inshallah it will be next lecture. Try to solve all the homework and continue your study. Also to look on the internet, and also to look for some useful reference. And see you. Have a good day.